Assalamu alaikum, everyone. So, today we'll cover a new topic, which is control of volatile organic compounds. So, last class, we talked about the volatile organic compounds and how we measure them. Now, today, we are talking about how we treat them. So, the control technologies that are available for the control of VOCs include carbon absorption, oxidation, condensation, and finally bioreaction. So carbon absorption is one of the most important and most used methods for the capture of carbon. However, it's a destructive or more destructive control, meaning that once you do the control, you end up having a waste that you have to deal with and it gets consumed. Yes, you can regenerate, but it's not the same. Oxidation is where you use fuel to burn your VOCs. Condensation is where you get the VOCs to condense in the liquid phase, so then you can collect them. And finally, biological or bioreaction is when you use microorganisms to feed on this VOCs to break them down into their elemental constituents. So in the first video, we'll cover the carbon absorption. So let's watch this video together about carbon absorption.
Studying adsorption, huh? Got a big test coming up? Staying up all night studying? Let's see how we can make sure you get some shut-eye. At first, adsorption looks like it's just stuff sticking to other stuff. But if you take a closer look, you'll see that there's more to adsorption than that. Adsorption is the adhesion of particles on free surfaces. Adsorption happens when atoms, ions, or molecules attach to the surface of a substance without entering it. They hang out on the surface. An example would be chemicals in a liquid sticking to a solid surface. If we zoom in closely, closer, almost, there! You've probably seen an image like this in your textbook before. Ions, which are chemicals with a charge that are attracted to soil particles. It's a bit more complicated than just stuff sticking onto other stuff. The outer sphere and inner sphere complexes are attaching in different ways. It looks like some of them can easily be knocked off or exchanged with other compounds in the solution, while others are holding on tightly. You can clearly see at this view how the hydration sphere surrounds the outer sphere complexes and not the inner sphere ones. Can you see what the difference is? Water! We call it hydration. Water is dipolar, which means a water molecule has a...
So hopefully you can watch the video on your own time on YouTube. Now, moving to
adsorption, huh?
the next. The activated carbon is a very common used material for adsorption. It's not common, it is the most used material for adsorption. There are a lot of companies that all their business is just to sell activated carbon, to activate the carbon and sell it. So the activated carbon is produced from coal, wood, nutshells, and petroleum-based products. What really happens is that we activate the carbon. So this is very similar to the one that you use in the barbecue when you're at home and you want to grill, or you are go in the desert and you want to have a nice time. But that's the same charcoal, same carbon. However, this one is activated. Activated means we get rid of any impurity that is within the carbon. How do we do that? We do that by heating up the carbon to 1100 Fahrenheit in the absence of oxygen. What does this do? This makes sure that there is no reaction happening. Remember when we talked early in the class that oxygen is strong oxidizer. So that's why we do it in the absence of oxygen, to make sure there is hardly any reaction that takes place. And then when we heat it up, any impurities on the surface of the carbon just leaves it. So once this happens, you will find out that the carbon itself has so many pores that are inside that got freed up. So let me tell you how it looks like. It looks like this. This might be your carbon granule before activation. I'll take this carbon and heat it up temperature to 1100. What will happen? All this impurities that were inside, right? They will leave the carbon without reaction, and behind it, or instead of them, there will be spaces that were occupied with the other molecules. So let's look here. Let's just take a very small part and make it bigger. So if this is the surface, now there were particles here. So these particles will start to leave like a pore instead of the impurity that was there. And then there were smaller impurities here, and then smaller impurities over there, and then here. And then this one has channels, and smaller. It's like a highway, that out of the highway you have exits. You go from the exit to large streets. The large streets go to smaller streets, to very tiny streets and you get a whole network by activation of the carbon that actually increases one thing. Do you know what it increases? When we, instead of having it like this on the right, we have it like this on the left. Can you think of what increases when we activate? One parameter. Pore structure, that's the openings. But yeah, but what is actually increasing when you are having this material? Got it? Surface area. That's actually what's increasing. Because originally, your surface area was just this. Now I'm making it large, right? This is originally your surface area. Now your surface area, look at how big it became. All of this became freed up as surface area. What happens when you have more surface area? The locations that are available for physisorption or chemisorption increases a lot. Right? If I have the surface of this desk over here, and that's the only available for me, I can length times width, I know exactly how much it is. Now imagine this has a lot of mountains and valleys, peaks and turfs. Then the surface area will be much higher. Now imagine this is microscopic, you cannot even see it. The pores, higher and higher and higher. Do you know the gram of this carbon? Gram, like it's something that probably as big as that. The gram of carbon, how much is the surface area? In any unit, can you think of what's the surface area? -6. What's the units? The units of area, like millimeter square, centimeter square, meter square. What are the units? Millimeter square for 1 gram. So the area is usually from 500 to 700 meter square per gram after activation. Meter square. So every gram has a surface area of 500 meters square. Can you imagine how much area is freed right now? It's basically more meter, yes. So it's more pores than solids. Make sense? So now we talked about the 2 types, the chemical adsorption, which happens with a reaction. It's usually irreversible. And we have the physical, which happens with forces, attraction, So this is an example of one of the attraction forces that can work on physisorption, the van der Waals forces. The van der Waals forces are forces that attract molecules of adsorbate, which is something that's being absorbed, to the molecules in the adsorbent wall. And it only happens, it's a very weak force. It only happens when the molecules are in the vicinity, very close to the surface. So these are micro forces that happen when you are really, really close. Similar to how you touch two surfaces together, and once they are very close, then they get stick together. Okay? So these are the van der Waals, what they call van der Waals forces. Here is how it looks like in reality when you have the surface. Here, I'm trying to make it in red. You can see you have something what we call the macropores. This is a macropore. Going into micropores, smaller pores. And there is sometimes something called mesopores, and so on and so forth. So what happens is that if you have two, here we have two contaminants, contaminant 1 and contaminant 2, the yellowish and the bluish, and they keep absorbing to the surface. Some of them find their way in, some of them even find themselves into the macropores, micropores, mesopores, and so on. Some of them are condensed. Condensed meaning that they change phase into a liquid phase. Some of them stay in the gas phase. Some of them are forming monolayer, meaning one layer only. Some of them can have multiple layers. So one compound can absorb on the surface, and then another compound can absorb on top of it. So that's also another property of. So the one very important thing that we need to know about absorption, it's its retention capacity. The retention capacity is the maximum amount of VOC that can be absorbed per unit weight of carbon. So imagine in the previous slide, if this is all has blocked. Here, this is blocked. Now here, all the surface is taken. It's all taken. Imagine that. What will happen? When another new molecules come, they don't find any surface to adhere to, they will just keep going. They will not stick to the surface anymore. This means that you got saturated. You got saturated. So there is no more space for another compound to adhere to the surface. And this is what we call the adsorption capacity. Once you reach the capacity, that means all the sites are blocked. And this is calculated in how many pounds of VOC are absorbed per 100 pounds of carbon, or gram per gram. So it could be pound per pound, pound per 100 pound, gram per gram, gram per kilogram. So it's actually a weight percent. Doesn't have a unit, yes. So the retention is a function of temperature. Usually, the retention decreases at higher temperature. Can you think why that is? So at lower temperature, here, you will have high retention, and at larger temperature, you will have low retention. Dissolves. You're getting close, but remember what the property that I told you, the one property I told you about the physisorption is that it is weak. What happens when you have high temperature? Remember the Brownian motion? Brownian motion, when the particles start to go and have like they transform energy into kinetic energy. So one particle will keep moving right, left, up, down. So they keep vibrating very much. So the higher the temperature, the higher the vibration of any particle. And since particles are trying to move at higher temperature, they can overcome the weak force of the physisorption, and then they can leave the surface. So that's why the retention at high temperature is lower than the retention at low temperature. It's also somehow applies to chemisorption because the reaction when you have low temperature can happen on a larger scale than also on higher temperature. So because at lower temperature, you can have more reactions, so more sites available. While at higher temperature, you don't have that much sites available, so the retention is decreased also in the chemisorption. It's all about, the retention is all about how many sites are available for the molecule to stay on it. So that was temperature. Pressure is another thing. So retention is actually increased with increased pressure. Can you think of a reason why this happens? Let's look back. Over here. Remember when I told you that this one gets blocked? Here, this macropore. What happens if we have high pressure? Pushing. So exactly, if you have a lot of pressure here, it's pushing everywhere. So what happens that some of the pressure will push these particles all the way inside. So basically, you are making sure that you are filling more and more pores. Right? Exactly what you do if you have a trash can, trash bag. Have you ever carried the trash bag and then it's full? Yeah, it's very full. So you push, you apply pressure to reduce the volume, right? So you can close the bag well and take it, or can take more things inside. So that's exactly what happens when you have higher pressure. You are pushing your particles to go places they wouldn't go otherwise. So that means you are increasing the retention capacity. So again, at higher pressure, you get higher retention. At lower pressure, you get low retention. So in this, I'm showing you a typical isotherm. Now, what is an isotherm? An isotherm is a graph that we try to make it between the concentration that's available and the amount absorbed. So imagine that we have a bottle like this. And this is an actual experiment that I have done it myself and a lot of people have done it themselves. So this is closed bottle. Okay, in this closed bottle, we have activated carbon of a certain mass, X milligram. And then we have concentration, C naught, of any VOC. So I do this bottle. I put, let's say, 5 ppm of benzene and with 1 gram of carbon. I leave it for some time. I shake it. I keep shaking it for some time. And then I see what happens. What do you think will happen? If I start with 5 ppm at 1 gram of carbon, what will happen after it reaches equilibrium? Equilibrium meaning I keep until it doesn't change anymore. What will happen to the concentration? Yes, it will. The concentration of benzene, that's benzene, not carbon, will decrease, right? Why? MashaAllah, because it's not available anymore in the gas. but it will actually now some of it will be on the gas and some of it will be on the surface of the carbon. So this 5 maybe becomes 0.5 after equilibrium. And we still have 1 gram of carbon. Where is the other 4.5? They are on the surface of the carbon. Okay. Now, what happens if I put 2 grams of carbon instead of 1? Or at least whatever will be in the gas will be less than 0.5. So let's say it will be 0.1 if we add 2 grams of carbon. So what will happen if we put 5 grams of carbon? Maybe the 0.1 will be 0.01 and so on. It will sometimes, yeah, you can take everything from the gas and it reaches 0. It will never be 0. It will be lower than what we can measure. Okay? So this is what I'm just describing to you. That's called isotherm. It's a description of the behavior between how much stays after steady state, how much stays in the gas, and how much is absorbed on the carbon. So this is very much here. The x-axis is the partial pressure, which is the concentration. You remember in gases, the concentration can be given as parts per million, also can be given as partial pressure. So that's the concentration on the x-axis. What is the amount on the y-axis? That's the amount absorbed in gram per gram. So gram on carbon over gram of carbon. Again, gram on carbon. So that's amount, how much became on the carbon, of benzene on the carbon, over the gram of the carbon itself, how much you started with. So you do this by doing a lot of series of experiments. You have lots of these bottles. You can change the initial concentration. You can change the amount of carbon. And you run them all at the same time. And then you leave them to reach equilibrium. And then you measure, again, the concentration in the headspace. The concentration, the final concentration. And accordingly, you get a point. So for every bottle, you get 1 point. And then you connect them together and get a graph like this. This graph is called isotherm. Now, that's another thing that we can change. We can do the isotherm at room temperature. We can do it at cold temperature or at hot temperature. The results will change because you remember the amount absorbed changes with temperature. So now let's assume at one concentration, at the same concentration, you can get more absorbed. I'm sorry. At the same concentration, let's say here 0.1 psi, you can get more absorbed on a lower temperature than on a higher temperature, which makes sense. That's what we exactly explained before. So you can do the isotherms, and the isotherms are also done at different temperatures. Another parameter that also affects the retention is the molecular weight of solvents. So now, if you have a high molecular weight, you will have more retention. If you have a lower molecular weight, you will have lower retention. Molecular weight of the particle itself that attaches to the surface. Think about it from, if you have a large molecule. This molecule only attaches to the surface with one part of it. So now we are having all of this and filling how many spots? One spot. While if you have smaller ones, it will take the same spot for a small volume. So when you have larger molecules, you are actually filling up the whole space with one spot, with one slot, with one location. While if you have smaller ones, it occupies the same space, but it's much smaller what you are what you are retaining. So that's how you get much more. Not always true, because if you have very large molecules, sometimes they can block the pores. Block the pores. So other particles cannot get in. Imagine you're playing basketball and then you get a ball that's not a basketball. So it sits on top, so nobody can score anymore. Okay, so also could go either way. Humidity. Water also attracts the surface similar to VOCs. So the water in the gas also competes on the slots, on the available slots, competes with the VOC. So now having water usually decreases the retention, decreases the capacity, because it's a competitor. So this is a typical setup where you get from left, from the here, you get your particles going through a filter. Why we have a filter? Not to clog the activated carbon. This is the activated carbon here. That. So usually we get a filter to make sure that anything that will clog the filter is left out. For example, sometimes humidity, sometimes polymerization, things that will polymerize. So they will just make a cake on top. So then it will just increase the pressure without being absorbed. So you get rid of things, okay, that you don't want here. And then once it goes to the bed, for example, here, this bed is very good at absorbing this yellowish one. So it retains the yellow and leaves the blue. So here, there was also a green. You see here, there was green, blue, and yellow. The green got stuck here. Exactly. The yellow and the blue goes all the way through. But while you are seeing here, why you see these colors? Basically, when the yellow starts to get on the bed, it starts to get on the top layer. So, and they start to fill layers as they go. This, imagine it as a column like this. This is all activated carbon. Now, this is just colors to show you the breakthrough, but it's not actually what happens. Actually, some very rare cases, this you can see that because the chemical reaction, the chemisorption changes color of the surface. That's permanganate. Sometimes it happens. That's what I'm saying. And if you're using permanganate surface and it reacts, it changes color. But this is very rare. Usually it doesn't. But here it's this just representation just to show you that this one is full. This one is saturated. Yellow is being filled. Available for absorption. Very good. In this case, it's just an example to show you that not every carbon or not every adsorbent has an affinity for all compounds. Not everything gets absorbed. There are a lot of things that gets absorbed, but not everything gets absorbed. Otherwise, life will be so easy, right? Unfortunately, it's not that much. So we will just stop this video here, and then in the next video, we'll be talking about the regeneration of carbon.